you all for having me. So yeah, I'm Anna Horleston. I'm a postdoc at the University of Bristol, and I've been working on InSight for, I don't know, 2.5 years now, I suppose. Well, more than 600 sols because I joined before we launched, so gives you some idea. So yeah, today I'd like to, if I can make the slides progress, talk you through the mission. So first up, why send another mission to Mars? And then I'll give you the background to InSight, our mission objectives, and the instrumentation we have on the lander. I'm going to focus on the seismicity and MQS, which is the Mars Quake service, because that's what I do with my time. And then I'll do a review of the primary mission objectives and the results we've got so far. And then we've got a nice little sound file of the spacecraft, because obviously it thinks no one's listening sometimes. And then finally we'll round up, as John said, with questions. So why Mars? Well, for a long time I thought this image of Mars was sufficient as a kind of why Mars. I mean, humans have always wanted to go to Mars. It's just an amazing place, and we've been able to see it hanging in the sky for, well, forever. And then earlier this year I was lucky enough to go and see, I don't know whether anyone knows of Luke Jerram's work, but he's an artist and he has created various massive artworks, including he did Gaia, which was a globe of Earth, which was 7 meters in diameter, and you could wander all around it. He did the same for the moon, and this year he did Mars. And literally the weekend before we went into lockdown, I was invited to a preview of it. And this is my 11-year-old who wants to be an astronaut, and he and I literally spent, I don't know, nearly 2 hours wandering around this model of Mars, picking out craters, looking at where the landing site was. Just amazing to get up close and personal and to know that we have the imagery to do that. So really, why Mars? Because it's inspirational and it's fascinating. So yeah, Mars, we've been there a lot of times. These are the historic robotic missions that we as the human race have tried to send to Mars. And I say we've been there a lot of times. Actually, we've tried to go there a lot of times. We've also failed to go there a lot of times. And hopefully you can read the text on these, but you know, we've lost things in launch, things have, you know, payload fairings have failed to open. There are a few things that missed the planet, and originally I thought that was kind of crazy. How do you miss a planet? But when you think about the actual mechanics of getting something onto a landing site, as we'll see later on, it takes quite a lot of precision to do that. But anyway, we've had a lot of successful missions as well, especially lately, and of course NASA had a lot of success landing on the planet itself and not just orbiting it. So here we've got obviously the Viking 1 and 2, Sojourner, Spirit and Opportunity, Phoenix, Curiosity, of course, which is still operating now, and now InSight as well. And of course, we've got what now 3 things in orbit on the way there. So fingers crossed there'll be many more things on Mars next year. So from these, we've obviously gained a lot of knowledge about the exterior of Mars. We got lots of beautiful images of things like sand dunes, of carbon dioxide ice, of little rounded stones, evidence of water flow. And this is brilliant, but effectively we've only literally scratched the surface or bounced things off the surface. And InSight, we want to go look at the interior. So the overarching mission tagline is that we want to understand the formation and evolution of terrestrial planets through investigation of the interior structure and processes of Mars, which we'll do using seismology, geodesy, and heat flow, which nicely wraps around to give our acronym Interior Exploration Using Seismic Investigations, Geodesy, and Heat Transport, otherwise known as InSight. And there's a reason we have acronyms at NASA, because let's face it, everything has a ridiculous name and needs to be contracted. So Mars. I said we know a lot about the outside of Mars. We've, thanks to seismology, we also know a lot about the inside of Earth and the Moon. And Mars is basically the middle ground. So we've had seismometers on the Earth for over 100 years. We've also obviously been able to explore it ourselves, to look at the rocks, to, you know, we know an awful lot about our planet, both the exterior and the interior. We know about all the beautiful differentiated layers we have. We know about subduction zones. We know about plate tectonics. On the Moon, we sent, so obviously based on our ideas that seismology was great for understanding the Earth, we sent seismometers to the Moon. So the Apollo missions carried seismometers, and for maybe 7 or 8 years, we had seismometers on the Moon. And from that, we know that there are quakes on the Moon, that they're different from earthquakes, that the Moon is pretty much solid and cold and dead, And that's kind of it. But that's, the moon is this size and the Earth is this size and Mars is right there in the middle. What we do know from all the external things of Mars is that it's big enough to experience a really active history, geologically speaking. I mean, we've got Olympus Mons, which is the largest volcano in the solar system, but it's like 20 kilometers high. And that's 3 times the size of Everest. We have a huge huge outflow channels, huge crevasses and canyons, that's the word I'm looking for, and craters and lakes and, well, all sorts of things, evidence of lots of exciting geology. But now it appears dormant, it appears pretty much frozen. So it looks like it was, you know, had all that heat and then it lost it all and it froze effectively. But we'd really like to see how that has manifested itself on the interior structure of the planet. You know, could it differentiate completely? Did it have time to do that? Does it look like Earth with, well, lovely clear layers inside it, or is there still a little bit of undifferentiated material inside? So that's really why I'm going to look at Mars, and then from Mars we can extrapolate with our knowledge of Earth and the Moon to other planets or other terrestrial bodies in the solar system and beyond. So our key mission goals, and these I will try to give you some answers to by the end. The size of the core, excuse me. So its composition, its state, whether it's liquid or solid, or as we say, partially dissolved. We want to look at the thickness and structure of the crust, the structure of the mantle. So we've got the crust around the outside, obviously the mantle here, the core in the middle. We want to look at the structure of the mantle and its composition, how warm the interior is and how much heat is still flowing out, and then the rate of seismicity and meteorite impacts. Now, that's quite a lot of things to try to do with one small lander and only 2 Earth years or one Mars year of data. Now, fingers crossed for an extended mission, but that's quite a lot to bite off and have a go at. But InSight is packed full of all the equipment that we need to do this. So I'm going to work my way around this image, and we will look at all the acronyms that we've come up with. So we'll start off with IDS. This is the Instrument Deployment System, which to you and me is a robotic arm, but it's not just the arm. The arm is actually the IDA. On the arm, we have the IDC, which is the Instrument Deployment Camera. We have the grapple, which is just like a claw on an arcade game, but we have better control over it than you do on those things. So it's designed to pick up things that all our instruments have, small knobbles with flanges on top that we can grab with the grapple so that we can move them around. We've also got a scoop, which is actually kind of a remnant from the fact that we stole this arm off another spacecraft, but it's proved to be very useful as in its own right. So scoop, grapple, arm, camera, all comes to make IDS. We have a second camera, which is down here, which is the Instrument Context Camera, or the ICC. You'll see a lot of images. We've taken, I think it's about 5,000 images now with the 2 cameras, but the majority of them have been taken with the ICC. It looks out across our workspace, so you can see the 2 instruments, and you can see the, you know, the planet in front of us, and we can get images of the sky and things like that as well from down there. So really, really useful cameras. Twins, originally named the Temperature and Wind for InSight experiment. These 2 white booms you can see here, these are literally wind sensors and temperature sensors. They do exactly what they say on the tin. So they point in opposite directions so that we can measure the wind on a full 360 degrees. And these are really useful for helping us to determine what's a seismic signal and what's a wind signal. RISE, the Rotation and Interior Structure Experiment. This is really cool. I have to admit, I kind of, I didn't know very much about this side of planetary science when I started this project. So hearing about RISE, I was kind of like, you're doing what? It's like a GPS system. So RISE is, they're 2 radio antennae. They work in X-band. They send signals directly back to Earth. And so they communicate with the Deep Space Network, who send a signal, bounce it back again, and the time delay and the Doppler shift of those signals tells us exactly where the spacecraft is, and if we know exactly where the spacecraft is, we know exactly where Mars is, and we know exactly how Mars is moving in its orbit. By measuring its wobble, its precession, we can measure the, we can extrapolate to get an idea of the size and state of the core. So a really cool experiment, but it does need at least 1 Martian year of data. We haven't even been around the sun once yet. So that we haven't got a lot of results from that yet, but it is, the results we have are great, but we just haven't got enough. HP cubed, the heat flow and physical properties probe. This is also known as the MOLE. Anyone who's followed the mission at all will know a little bit about this instrument because it comes up a lot in the press, even though it should be going down. It's doing a lot of coming up. This is a self-propelling probe. So within it, it has a mass on a coil, which is wound up, and then it hammers on the bottom of the probe, inside the bottom of the probe. And the idea is that it will hammer its way down to 5 meters. Within it, it has a heater and temperature sensor so that it can put out a heat flux and measure how that dissipates. So you can get the, what's the word I'm looking for, heat capacity of the soil. And also the entire tether, this entire cable, is instrumented with some, thermic sensors so that you can measure the temperature all the way down. Now, this, like I say, was supposed to bury itself 5 meters, and it has not successfully done that. And we believe that to be basically down to the type of soil we've landed on. It's a bit like a British rail, wrong leaves on the line. We've hit the wrong kind of soil, and there's not enough friction for the probe to descend. So we're still working on that, and I will show a picture later. APSS is the Auxiliary Payload Sensor Suite. This includes a magnetometer, an IFG, and the pressure sensor so that we can measure the atmospheric pressure. And these are really, really useful to help us distinguish anything else from the seismic signal. And I've come to SEIS last because, well, A, I'm biased, but B, it is the key instrument of the mission. So SEIS actually stands for the Seismic Experiment for Interior Structure. What you can see here is actually the the wind and thermal shield, WTS, another acronym for you. But underneath that is our seismometer, which is it's actually super, super sensitive, and it's got 2 instruments inside it. One was built by the French and is a very broadband sensor which measures the lower frequency components, and the other is made up of 3 components that were made here in the UK, designed at Imperial College, built by Oxford, at RAL Space, and tested in Bristol, which are etched out a single silicon wafer, each one of them, and they're called the SPs. And those, so between the 2 of them, we have a full spectrum for looking at seismic data. So that's the instrument schematic. This is the instrument itself in reality. So here you can see the wind and thermal shield. Here, that's the actual seismometer size. Here's HP cubed inside its housing before it, so that's how we get it to the ground. Here are the radio antennae for rise. Here's a wind boom, the twins. Here are some people, just to give you an idea of scale. And here are the solar panels, which are about 2.5 meters across. So I think these are some of the biggest solar panels we've ever sent up to Mars. So this was the spacecraft on the assembly floor. I'm not going to show you launch photos because actually it was really, really foggy. So all I could see of launch was what you could have seen on TV. I could hear it, but unfortunately, we weren't able to see it at all from the field that we were in watching it. But I can tell you where it's gone. So here is a topographical map of Mars. We actually have the best topography of Mars. It's the best topography of any planet in our solar system because there's nothing to get in the way of our lasers. Well, maybe some dust storms, but not at the moment. So here we've got the volcanoes I talked about. Here's Olympus Mons. Here are the Tharsis Bulge. We've got Hellas crater here. To give you an idea, I realised I haven't put a colour scale on this. Hellas is about 8 kilometres deep, and Olympus Mons is about 20 kilometres high. So above the datum. So blue's low, white is high, red is high. And you'll notice that most of our landers have been sent to the kind of equatorial regions and north of, this is what we call the hemispheric dichotomy, where the northern part of the planet is seemingly younger, it's lower, and it's, there are very few craters on it compared to the southern part of the planet, which is much higher topographically and is much older and covered in all these craters. We like to go to smooth areas, but the primary reason we're near the equator is for solar power. So you saw we had huge solar panels. We've got a lot of instrumentation to power. We need to communicate regularly. And so we need to be where we can recharge our batteries. So that's why InSight is going here. And to focus in on the landing site itself, here is InSight's landing site. Here is Elysium Mons. So this is another extinct volcano. We're on Elysium Planitia, which is an ancient volcanic plain. It's Surface age varies from about 3.7 gigayears to 2.5 millennia, so it's relatively old. And we think there's a nice basaltic layer a few meters below us. And we've got a couple of areas of interesting geography. Now, Cerberus fossae in particular is about 1,600 kilometers away. This area contains faults, and there's evidence of volcanic flow and perhaps liquid water outflow channels with ages as recent as 2 to 10 millennia. We've also seen in recent imagery from Mars rock falls within the Cerberus fossae, which could not occur just, like from wind. The wind is not strong enough to knock these kind of rocks over. Wind is not really strong enough to knock any rocks. So if there are rock falls and fresh rock falls, then that is an indication of seismic activity. Basically, something came and shook those rocks down. So seismicity seems like the most probable answer there. So the exact landing location, for anyone who likes to know these things, is 4.5 degrees north and 135 degrees east. And relative datum, we're actually 2.6 kilometers below zero. And that's partly because we needed as much atmosphere as possible to slow us down on the descent. But the Elysian Peninsula has also been described as one of the most boring places on the planet, because we didn't want, well, we wanted to go somewhere where we could safely land, but also where we could pick up signals from further away rather than being dominated by something very close. So this is the landing site itself. Now, I said I was surprised when I heard that things had missed the planet. This ellipse here is 140 kilometers long and about 40 kilometers wide. The red dot is where we landed. These are all obviously craters and other rocks and things which we wanted to avoid. Now, for us to have hit just this ellipse, never mind this red dot, for us just to hit this ellipse here, is, I had this quoted to me, it's the same as, so I live in Cardiff, my sister lives in Philadelphia. It's the same as me throwing a baseball from here. Obviously, this was told to me by an American, so probably let's call it a tennis ball. I'm sitting in my study here. I throw this tennis ball to my sister in Philadelphia, but I don't just aim for Philadelphia. I need to aim for the full stop key on her laptop, on her desk, in her study, in her house in Philadelphia. And that's a pretty, pretty precise target. And I admit now with spacecraft we have trajectory maneuvers that we do in space, so it helps us get to these places. But I was still super impressed when we managed to even hit that ellipse, and even more impressed when 7 minutes or so after landing we got this image. Now, I'll admit a lot of people are underwhelmed by this image because it's dusty. Now, please remember we've just retro-dusted into a very dusty planet, and this is the ICC, so this is on the bottom of the lander. So we landed on November 26th, and you can tell you a little story about this rock here. This is one of our feet. We've got 3 legs. This is one of our feet. This is a rock. Now, we were told by the geologists that there was a 1 in 52 chance of us hitting a rock on landing. We got within, what is this, about 2 feet of a rock. But this rock is known as the Ace of Spades rock, because given that 1 in 52 chance, Tom Pike, so the PI of the short period instrument I told you about earlier that was made at Imperial College, Tom said to his postdoc Konstantinos, if we are hitting a rock, that's like you picking the Ace of Spades out of this deck of cards. So I think you can all guess what Konstantinos picked out of that deck of cards, and this is the Ace of Spades rock, at least within the team. May not have been publicly named that, but that is how we know that rock. So that was our first view of Mars. Our second view of Mars was from the IDC, so the instrument deployment camera. So here you can see the instrument deployment arm and the scoop, and here's our lovely grapple. Here is size, the seismometer. You can see how well engineered we are with our nice springy legs here. So we're all sat on the lander. And this gave us our first view of where we'd really landed, not just a dusty field of a dusty lens cap, which is effectively what we saw in the last one. So what we've landed in is it's basically a degraded impact crater. It's about 25 meters across. We've nicknamed it Homestead Hollow, and it's basically infilled by impact generated sediments. So the crater formed, and then other sediments have just been blown or ejected into it. Now you can see, if you look in front of us here, it's quite smooth, and you can see in the distance there are other areas like this, which are again other degraded infilled impact craters. You can also see that between these areas, there's an awful lot of very rocky material, and this could have given us a really bumpy landing. So we're really quite lucky in where we landed. including this particular rock, which was quite rapidly nicknamed Dwayne Johnson. For anyone not aware, that's the rock. So it also gives you an idea. We were looking to land as level as possible. That landing area had been analysed so that we would hopefully land somewhere with no more than a 15-degree tilt. If you look at our horizon here, we do have a little bit of a tilt, and our lander is at 4 degrees, so it's pretty good. We also know from imagery of here, obviously we can see this crater has been infilled, but from other fresher craters, we know that there should be a rocky layer of an ancient lava flow with about 3 to 5 meters depth. So we're hoping to be able to image that with the seismicity, and we thought we might encounter it with the mole, but obviously we haven't descended that far. So here we are on Mars. And because we can, we had high rise from the satellite camera go over and take photos for us. First of all, it should be noticed that obviously nothing is green, that's just saturation of the camera. So we have, here is the heat shield, which fell on the edge of a crater, not a place that we would have wanted to land. Down here we have the parachute, and I love the fact that you can actually see the entire parachute. You can tell the direction of the prevailing wind. So this is the back shell that would have been attached obviously on the top of the craft with the parachute coming out of it, and you can see the slight dust cloud that's been kicked up here as it's just knocked off the surface dust. And here is InSight, and you can tell again this is InSight because we have this lovely circular dust pattern where we've retro-thrusted our way down and blown away the surface dust. The very reflective green spot here is our wind and thermal shield, which was that white dome, which was then placed over the seismometer on the ground. And the 2 black lobes are our solar panels. Obviously, this was taken after we'd landed, a few weeks after we'd landed, and the solar panels were fully deployed. So we know exactly where we are, and you can get an idea here of what a degraded, ours is quite obscured by the dust we've kicked up. But for example, here you can see the outline of a crater, but you can see that this is relatively infilled, certainly compared to this kind of a crater here. So we're on something like this, but it's just hidden a little bit underneath our dust cloud. So there we are, we're on Mars. So let's look, what have we actually been doing since we got there? Well, my job, I work for the Mars Quake service. So the mission has 2 primary output services. We have the Mars Quake service and the Mars Structure service. In fact, we have subsequently created the Mars Weather service as well, because it turns out the weather data from all those auxiliary instruments we sent is really fascinating. So the Mars Weather service now exists as well. But originally it was going to be Quake service and Structure service. The Quake service is there to detect and catalogue the seismicity so that the Mars Structure service, MSS, can then invert it for the internal structure of Mars. So MQS, we have a dedicated team of 10 frontline seismologists. We take in shifts, so we work maybe 2 or 3 days in a row, and we are then basically on call. So the data comes down, we get an email alert, and we look at it within an hour or 2. Typically the data is within about 12 hours of its collection on Mars. So right now I can get data from, in fact I think there's data from 6 o'clock this morning on Mars, so it's quite good in terms of being near real time. We're not at a point where we can simply run an auto detection algorithm. So obviously an Earth-based Quake service, everything is pretty much automated until something is detected, and then a seismologist will go and review it. We can't do that. We've actually got to go and find things, and I'll show you why in a minute. So the team is headed up by ETH. They've developed a whole suite of tools, and we've got a variant of size comp, and we've got a lot of things that we look at when we look at the data. The first analysis we do is in the daily spectrogram. Now this is a typical day on Mars. So let me just talk you through this graphic, because if you've never seen one before, it can take a while to get your head around it. So first up, we've got here, this is the actual raw waveform from the 2 seismometers, the SP and the VBP. Below that, we have this axis is frequency. Because we're seismologists, we don't like decimal points. So once we get below 1 Hertz, we go into period instead. And we've got the time axis along the bottom. So we work on these, we work on Martian days. So we start Martian days since the mission began. So that's a solar Martian day. This was Sol 184. So 184 days of Martian days since November 26th. And we plot these so just from an hour before midnight to an hour after midnight, so that we have a bit of wraparound when we flip through them. And we also give time in UTC here. And what this plot actually represents is the power spectral density. So we have basically the color, it represents the amplitude of the signal at that frequency. frequency. So yellow is a much noisier signal, blue is a lovely quiet signal. Now, most of the days, certainly early on in the mission, when we first had the seismometer up and running, showed a very similar pattern like this. So you would see that in the middle of the day, you'd see lots and lots of noise. This is wind-generated noise. And then in the early evening, we'd see a quieter period, and then during the night, the wind would kind of pick up again. But it's quite a different wind regime to what we see in the day. And I say this is partly why the atmospheres team have set up the whole weather service, because it turned out this wind data was fascinating. There are a few characteristics that stand out in the seismic data. So these horizontal lines or near horizontal lines are lander modes. So the lander has known resonant frequencies. So as the wind blows, these are excited and that signal travels straight through the ground to our seismometer. Some of these are temperature dependent. So obviously this particular one here is temperature dependent. So it dips right down during the day and then comes back up again. You'll notice they often disappear here. This is again how we know they're lander modes, because they disappear when the wind drops. So as it gets quiet, we lose the lander modes. There's an enigmatic mode, I can call it, nothing else, at 2.4 hertz, which we see here in low wind conditions. We don't really see it during the middle of the day, but we see it here when none of the lander modes are triggered. We see the 2.4 hertz mode. So this may be some resonance potentially of the solar panels, but it may be a geological resonance. So the shape of the crater underneath us, for example, may be resonating at this. The 2.4 hertz mode is interesting in terms of our event analysis, because we often see events which show as an excess excitation on this 2.4 hertz mode. So you'll see a bright spot here, and it's an event, a seismic event, or at least that's how we're categorizing them for now. So that's a basic day. The other important thing to notice on these are these vertical stripes, very bright stripes you see here. These are glitches. So these are instrumental effects, normally caused, we think, mostly by, there are a couple of reasons. There are things where the lander cracks and makes a noise, which is transmitted down to the sensor, but also changes in the surface temperature around the sensor cause tilts on the sensor, which cause sudden jerks and cause these glitches. So the first thing we do, as I say, at the Quake service, is we try to find quakes in spectrograms. So here's another day, and here we've got 2 Mars quakes. So this is broadband event, and this is, I think this is categorized as a high frequency event. I'll talk more about the frequencies in a minute, but they stand out quite clearly. They're very different from the wind noise, which is as kind of smoother noise. And also, if you saw the 3 components, I'm only showing you the vertical component here. We've got 2 horizontal components as well. You'll see that when we have wind, the horizontal components are highlighted. So here, for example, there's wind, and this lander mode is excited as well. But the lander modes do not show any particular excitation here where we've got these events. So that's 2 events. Here is another event. This is actually one of our best events. I don't know, looking at this, you might all go, what? This is why we have 10 of us who've been trained over the last 2 years to do nothing but look for these, basically. So yeah, these are, that is one of our best events. This is the Sol 173 event, and I will show you this event in more detail. And this is the first event we broadcast. So it's here. Now this one is hidden within the noise. This is a high frequency event, and it's, yeah, it occurred in the middle of the day. And at first sight, you're kind of thinking, well, how can you possibly find that? How do you know that's an event? And obviously we can look at the waveform, and I will show, and I won't show you that, but I will show you, I do show it to you. No, I do, here we go. I do show it to you. Here we have, it's got a sound file as well, which is the other way we can listen to this. So I'll play this in a minute, but I'm going to talk through it first. So here again, we have got we've got 2 sensors here. So we've got the VBB and the SP. So this is the very broadband instrument. This is the short period instrument recording the same thing. What we've got here is you can see wind, and then you can see what we believe to be the Mars quake here, or what is the Mars quake, and then we have here a signature of the movement of the robotic arm. So this was a day when we'd got a planned movement of the robotic arm, so we know exactly when that happened. And what I wanted to do, I'm going to play the sound file, hope it comes across, and we will just listen, and you'll be able to see how clearly we can hear that. I mean, you can see it quite clearly in the spectrogram here, but let me turn up the volume up and I'll play this. This is wind. And that's the Mars quake. Here's wind. Here's the arm. So what you can see from that is that although in the spectrogram it wasn't the clearest of signals, we could find it, once we thought we knew where it was, we could look at it and see it clearly in the waveform, but then we could also create the audio file, and it sounds so distinct from the noise and also from the robotic arm, which is a signature that we see quite a lot in the seismic data, but we always know when the robotic arm's moving. It doesn't do anything without us planning it. So yeah, a really clear example of the sound file. There are, oh, that shouldn't have played twice. We do have sound files from some of the lower frequency events, but it just won't come across over here. You'll need really good headphones with lots of bass. So because our events are evident at different frequencies, our classification system is based around the dominant frequency of the events. So we have low frequency events predominantly below 2.4 hertz. So here we have an example of a low frequency event. That one I showed you earlier, 173, that's a low frequency event. We then have broadband events where the energy is above and below 2.4 hertz. So they're mostly below, but they will have a hint up around the 2.4 hertz as well. So that's a broadband event, but we put the low frequency and broadband events into one family of what we call generic low frequency events. We then have a family of higher frequency events. So we have events that only excite the 2.4 hertz resonance. We then have high frequency events like this one, which excite the 2.4 hertz resonance, but also go above. And then we have very high frequency events, which go a much higher. They're often shorter duration, and they show a strong horizontal signal compared to vertical. And I'll show you an example of these later. We also have SF events, super high frequency events, which are much shorter in duration, only 30 seconds or less. And they are typically in frequencies 8 to 15 hertz, no energy at the 2.4 hertz. And we think these may be thermal quakes of some sort, but we're still investigating those. We also originally had a category called strange events, which was almost anything else we could identify that wasn't really seismic. And we catalogued those basically so that anyone else coming to look at the catalogue knows that we found this thing, but we don't know exactly what it is. In fact, there are very few of those now because we've now reclassified as the mission went on. So originally there were more of those, and then we've classified them into other things like the SF events. So we produce a catalogue, and the catalogue is released every 3 months with a 3-month lead time on it effectively. So we released a catalogue in July, which was data up to March. At the end of September, we'll release the data up to the end of July. So at the end of March this year, this is the number of events we'd seen in our catalogue. So we'd got, out of the low frequency or broadband family, we've got about 41 events, which only 2 are quality A. So again, we've got qualities of events. Sorry, I didn't mention this earlier. The quality is based on the signal quality, basically. So signal to noise ratio, and then whether we can see 2 clear phases. For anyone who's not a seismologist, with a seismic event, you would normally see a P arrival, so a compressional P wave arrival, then a shear a secondary wave arrival, and then a decent quake will then have subsequent reflected phases, but also surface waves. Now for us, we're content with a P and an S phase. If we've got a P and an S phase and we've got polarization of those so we can tell the particle motion, then we call it a quality A. Quality B, we may have 2 phases, but they're not as clear, and all the way down to quality D, where we know it's a seismic event, but we can't clearly pick phases. So these are just your rough numbers. The catalogue, like I say, is publicly available, and it's obviously increased slightly since then. But so the interesting events are our 2 category A events. So this is a low frequency Sol 173A. We're really original with our naming, I'm afraid. It's basically the day it happened, and then if there's more, well, everyone is then catalogued with an A, B, C, whatever, depending on how many we see each day. So S0173A, the first event we spotted on Sol 173. And here I've even marked the P and S phases. So this is just the vertical component, but you can see we have 2 clear arrivals, P phase and an S phase. And if we compare this to an earthquake, this is a figure made by my colleagues in ETH. And so they've taken earthquakes recorded in Switzerland, obviously, because that's where they are. So this is a Swiss earthquake, normally lasts about 30 seconds, short, impulsive quake. An earthquake, a teleseismic event they've recorded at 2,500 kilometers distance, has more of this kind of a shape to it. This is our Mars quake. So we've got a clear P and S arrival, lasts about 15 minutes. If we look at a moon quake, we just see this big fat kind of cigar shape, and it lasts for over an hour, and they just resonate and resonate and resonate. So you can see we're kind of somewhere in between these. We have this resonance signature that we have from the moon, where we have a really thick regolith of broken up material that the signal just bounces about all over the place. So you see the signal seeming to arrive from all sorts of places because it's bounced everywhere, every which way to get to you. Whereas on Earth, things usually travel relatively direct path to get to you. On Mars, we seem to see a combination of that. So we have an idea of the crustal structure, and it appears to be quite broken up, but not as bad as the moon. That doesn't sound very scientific, but it's pretty much where we're at. The exciting thing about the 173 and the 235b events, so those two quality A events, I said, we've got two really clear phases. We've also got polarization. So we can look at the particle motion to tell us which direction the event has come from. And both of these events, so this obviously is a map of Mars, here's InSight. We zoom in into this box. These two ellipses here show the probability density function of the location of those events. So these are the most likely places that each one of those events is. Both of these ellipses cross or are crossed by Cerberus fossae. So it appears that both of these events come from Cerberus fossae. Now, we have a third event, which we have one clear polarization on one of the phases, but not on both, which is likely to be over here. So again, same direction, it's interesting. But these two from Cerberus fossae, like I said, Cerberus fossae is a network of channels. They're about 1,000 kilometers long, but only a few meters to kilometers wide. Really narrow, but as I say, we have recent imagery of rockfalls. So we expected this to be seismically active, and it appears that it is. So this is really exciting for us. For anyone who's worried about the orientation of this, north is off to the right. So flip it around if you like to think of things in a standard map projection. It doesn't fit on the screen that way. So the other way we look at our events, now we've got two events that have two really clear phases, those P and S phases, is we often look at things by looking at the envelopes and frequency domain. So one of the problems we have with the seismic data is I showed you those vertical spikes, those are glitches. Now glitches cut across everything and overwrite any signal that might be coming from the quake. And these can be a real pain if you're trying to look at the time series of the data. But if you kind of cut them out and look at the frequency, we can look at the envelopes. So we can get an idea, you know, those big cigar shapes I showed you, we can then look at that in terms of the frequency content, and we can create these envelopes based upon the couple of events that we've got really good knowledge of the event, the 173 and the 235. We can do what we call alignment. So seismologists, we usually align our events based on the difference between the P and the S arrivals. So you have your standard velocity model, say P arrives here and your S arrives here, you can tell exactly how far away it is. So if we do that with all the other low frequency and broadband Mars quakes that we have, we can get an interesting picture, because they fall into three different categories. So we have a couple of events which have a good signal to noise ratio. They have an S minus P time between 25 to 30 degrees, and then again between 55 to 65 degrees. Two clear phases observed at these distances. Now, they might not look clear on all of these plots because they've been scaled relative to this S arrival. So sometimes the P phase is not that clear, but believe me, there is a P phase for these. We then have this section of events in the middle here between about 40 to 50 degrees, where we see a P wave. These, again, you can't tell that these max P wave, but they do, I promise you. They match the P wave and only a little hint of, or you know, or maybe no S phase. So we believe these to be within that 40 to 50 degree range. So there appears to be some kind of S shadow zone. So this may be a low velocity layer, but it may just be simply that as the velocity increases, there is a range where the S waves, it's not necessarily, not particularly a low velocity zone. It's just that the geometry just doesn't work for the waves to travel to us. We also have a set of events where we have either a very small or no P wave. Now, based on the idea that high frequency P waves would be attenuated over a greater distance, we categorize these basically as just being far away. We don't have any particular distance on these. Sometimes we calculate a distance based on the length of the coda of the S, so how long that S wave exists for, is in existence for. But we often don't even give a distance because we don't have a P phase, so we can't work that out. But we just say they are further away because they have no P phase. I realize that's a little hand wavy, but this is an entire different planet, so we don't have a good velocity model, and we don't really know. Well, we're learning every day what we're looking at. So that was the low frequency events. The high, I said the other major family we have is the high frequency events. So here again, this is an example high frequency event. So we've got a cutout of the daily spectrogram. So I've only gone from 9 AM to, actually we've gone 9 AM till, goodness, where have we gone till 9 AM? Where's a full day? The event itself is here between these white lines. And then we've zoomed in on that here again. So these plots here are zoomed between these dotted lines. The actual event is between the dashed lines. And you've got the waveforms here for the Z, north and east components. So you can see, like I said, we have two phases arriving, but these are more cigar-like in their kind of, they kind of bulge rather than the impulsive phases we had on the low frequency, the really nice low frequency events I showed. So here we call these phases PG and SG because we think these events are occurring within the crust and then reverberating their way to the seismometers. So they're relatively local events and they are crustal events rather than mantle events. So that's an example of an HF event, a high frequency one. This is an example of a very high frequency one. If you remember, I said that they had a dominant signal on the horizontals, so you can see it very clearly on the spectrogram here. They just really saturate the top of the scale here. And again, you can see it here, these are all to the same scale. So the vertical, you would hardly pick this up, but on the horizontals, it's really, really dominant, the signal. Here's an example of a glitch. In fact, these red boxes mark areas of glitch that we've annotated. There is a red mark for that one as well. So that's what a VF event looks like. Now again, we can use the envelopes of these and we can stack them. We've got over 400 HF and VF events, so, or HF and 2.4 Hertz events, so in this high frequency family. So we can do distance alignments for those based on the difference between those two phases, the SG and the PG, but also on the lengths of the envelope, again, a bit like we did with the S phase ones where we didn't know where they were. What we've seen is that, yeah, most of the events have two peaks, only a few show one. The ones, in fact, with one peak here, we've interpreted as being closer, just not having time to dissipate as much. They often have a shorter shorter coda. And we use an average crustal wave velocity to look at these distances, but we have a problem with our models for Mars in that most of our models have looked at the mantle and major mantle bulk compositions and pressures and temperatures. But the crust is a real unknown, and we have a great deal of uncertainty in our crustal models. But the coherency of the waveforms for all these events suggests a common origin. And like I said, we think that the high frequency family within the crust and the low frequency family below the crust in the mantle, and perhaps with this low velocity layer, but perhaps not even that. Another reason we think these are deep is that we've not seen any surface waves. So these are characteristic on Earth. We see beautiful surface waves. Those are the ones that do all the damage to people and buildings. But we're not seeing any surface waves for any of our events on Mars. So at the moment, we believe that that's probably because of the depth of the source. So this is our best interpretation of the seismicity at the moment. One thing that has a huge impact on our seismic observations is the atmospheric effects. So I showed you a single daily spectrogram before. What you've got here is, you see here, we've got Sol number increasing. We first had the seismometer fully operational on Sol 70. So this is approximately where this starts. Each single line here is one of those daily spectrogram plots. So you can see when we first deployed, we had quite noisy quite a lot of the day, but none of the real high intensity noise. Here we built up quite a lot of high intensity noise in the middle of the day. Here we had solar conjunction, so we didn't get any data because the lander was on the opposite side of the sun. And then we continued as well. So you see this is sunrise and sunset. So you can see how the noise drops off about an hour before sunset every day and normally gets quieter. So this is for the period that we've now just released the catalogue. And these are all our quakes, and you've got different symbols for all the different types of quake and different colours for the quality of them. And you can see that our quakes arrive, or we observe our quakes, in the quiet periods, because this noise is just too much. This is the 128 event here. It's about the only one that kind of goes into the noisier day, but you can see this noisy day is nothing like this bit here where this was really noisy. So that was how life was. This is how life is now. So this is our most recent one. This goes up to today. And you can see that the seasons have changed. And we are now seeing that where we had this beautiful, solid, noisy bit and quiet bit, we're now seeing noise scattered all the way across the day. And that we can even have our highest noisy parts at the parts of the day where we previously we're seeing our quietest parts. So all our events are basically, I've not shown you the latest catalogue, but that previous catalogue had all the events in here, and I can tell you that we're not seeing much right now. It's very quiet for the Mars Quake service, which, considering it's August and we want to be on holiday, is quite good, but it's not good really, because we'd love to be able to see the seismicity. Great for the atmospheric people. This data is giving them up. Yeah, they're having a field day, I'll tell you, but not so great for us. Another way we look at this is, so here, you're effectively seeing the same thing, but we're just looking at it in a different way. So we split our days, we based this plot around this kind of time of the mission. So we split the day into what we call, this has lost the key, sorry, noisy, this was the noisy night time. So this was, sorry, this was the quiet time. So this was that beautiful blue time, and this was between about 4 p.m. and 9 p.m. on Mars. This was the noisy night, which was after that, so from about 9 p.m., 10 p.m. through until 5 in the morning or something. This was the early morning, and this was the noisy day, so after, between sunrise and sunset, effectively. And you can see that relative to these noise levels, so this is the power spectral density of the noise, and then these are our events overlaying it. So this is at low frequency. You can see most of our low frequency events occur when we have this really quiet noise period, and they all pretty much come above the night noise, the early night noise as well. And same for the high frequency events. This is all of those 2.4 and high frequency events plotted on here. We saw lots of them here. But what you'll see is that in the last 100 days, the weather has gone mental. So breaking the day up into these categories means nothing. Our quietest periods here have now just skyrocketed. Our noisiest period has dropped down. It's, yeah, just crazy. In fact, now this I realize this has been replotted to just give us the lowest 10% of the time at the bottom and the 90% of the time. We had one before with the time windows, and they literally just crossed over. The top plot here shows you the tau measurements, so an indication of the opacity of the atmosphere, and the blue plots are the number of dust devils that have been recorded. These are recorded as pressure drops on a pressure sensor. We also see them in the seismic data. And interestingly, there weren't very many pressure drops observed in the previous noisy part, and even now it's just really variable. Some days you'll get hundreds, and some days, well, not hundreds, but where is the scale on that? Yeah, 50, 60. And other days you'll get maybe only 10. So it's very variable. The pressure, the atmospheric is it's really exciting for the atmospheric team, but really horrible for us on the seismic side. So the seasonality of the seismicity at the moment is being dominated by this the seasonality of the atmosphere rather than the actual seismicity itself. So summary of the seismicity today. We've had 482 events in the high frequency or low frequency families. We've also had 789 super high frequency events detected, and these we think may be thermal, so they are in a slightly separate catalogue from the other ones, which we think are more tectonic events. Most events show two energy pulses, so these are thought to be either a P&S phase or a PG-SG phase if it's in the crust. Only 2 events show clear polarization on both phases, and both of those events appear to come from Cerberus fossae. we've got no clear surface waves, we've got a possible hint of reflective phases, but not enough to work on, and we have a possible seasonality, but like I say, that may be due to the weather. We're also lacking really large events. Now, I realise I'm running over here, something drastic, so I'm going to be really quick through my last slides. I hope you'll bear with me. I said I'd recap on the previous objectives for everything else. So the first bit, core, crust and mantle, is a really short answer. It's a work in progress. So RISE needs at least 1 Mars year, and we haven't got that far yet. And we also might see a seismic signature from Phobos, which we can also use to constrain the state and size of the core. But again, we need to stack the years of data for that. The crust, we have some ideas. So we have been able to use what we've got and the actual simple sitting of the sensor and the HP cubed hammering data, which suggests that the regolith is very thin. It's a few meters compared to the kind of kilometer we have on the moon. And below that, we have more consolidated material, but the basaltic layer that we expected to be there from satellite imagery appears to be highly altered or fractured. We still don't know the actual depth to the moho, so that's the bottom of the crust. We could do with some bigger events to help us figure that out. The mantle structure, we've managed to rule out some of our a priori models, but basically we need bigger events, seismic events, to come up with that answer. The heat flow and interior temperature, well, this is the mole as of yesterday. It shouldn't be at all visible. We've done our best to hide it by covering it in soil. Unfortunately, the probe descended part way, came back out, descended, came back out, descended, came back out. We poked it, we prodded it, we've pushed earth on top of it. Next thing is to, now we've pushed earth back on top of it, is to push the scoop back onto the top here, and we'll push this back down to here, and we'll try hammering again. But we don't have our beautiful heat flow curve, which we hoped we'd have by this point. As far as meteorites go, the impact rate, we did detect a new impact. We have a new crater that formed. It's about 1.5 meters wide. It's 37 kilometers from the landing site. It arrived while SEIS was operating, but we can't see it in the seismic data. So we can basically say that the expected impact detection rate now has been downgraded from where it was when we thought we might see 5 to 10 in a Mars year, in an Earth year. Now we think it might be 2 in an Earth year. We haven't, as I say, we haven't had conclusive evidence that any of our seismic signatures are an impact yet, because the only impact crater that we know of that's arrived, we can't see a signature for. So that's just been published if anyone wants to go read up on that. For the seismicity rate, we have managed to come up with something for this. So here, this is looking at the low frequency events on Mars. These are the observed quakes on Mars. These are shallow moonquakes for reference. This was our prediction for Mars, but if we extrapolate our low frequency events to the whole of Mars, because obviously we're only looking at one small area of it, then we get this, which is somewhere near our predicted. These are the ones for Earth, so this is the global Earth numbers. This is the intraplate, so in deformed plate, intraplate areas, and this is in stable, so cratonic plates, so like the middle of Canada or something. And this is where our high frequency events lie all the way up here. So we've got an idea about how the seismicity is going. Again, it would be good to see for a whole Mars year. And I've got one crazy sound file I'd like to play for you. So I don't know whether, yeah, if a lander calls on Mars, can anyone hear it? The answer is yes, we can. These are the glitches, the dinks and the donks that we see in our seismic data. And basically it is the lander going from maybe 0 degrees to minus 100 degrees, as it does every day, and contracting as it does. And this is what we see in the seismic data. So this is our seismic record sped up to an audible level. But this is what is interacting with our data when we're trying to see seismic signals of tectonic origin, not of a lander origin. It's a bit of a crazy cuckoo clock going mad here. But I'm aware of the time, so I'm going to skip on. But if anyone wants to go find that, it's on the NASA website. And thank you very much.